Are live? Okay. So hello everyone. We are going to continue on the topic of memory-centric computing. My name is Geraldo. So I'm a PhD student here in the Safari Research Group, devised by Professor Onur. So I'm going to graduate soon. And if you ever want to reach me, or if you are interested in anything that I'm going to talk about here, feel free to send me an email. And I do research basically in computer architecture, and I've been doing research on processing memory architecture since 2016, so many years already. So before I start with the topic itself of this talk, I'm going to briefly remind everyone of what we are going to talk about here. So the problem that we're trying to solve, Onur already covered quite well, of course, during the keynote talk, but just as refresher in case you forgot because the croissants were too delicious. So the current problem that we have in today's systems is that we are wasting a lot of throughput and a lot of energy moving data around in your system. And the reason of that is because we are processing in a centralized way, which is really far away from where the data resides. So it happens in different applications. For example, this is that paper that Onur mentioned from the Google server workloads, and they show there that the majority of the execution time was spent doing data movement. And in terms of the energy, this data movement creates a huge problem because moving data around takes way more energy than computing on the data itself. And this impacts the total execution, or the total energy expend in systems quite significantly. So the way to solve this is that we need a paradigm shift, which enable us to do computation with minimal data movement and compute where the data makes sense in a more data-centric way. And by doing so, we can basically minimize this trip latency from the main memory or for other memory components in the system, reduce energy consumption, and overall improve system balance. So there are different ways of doing this. What we are going to cover here is what is called near data or processing memory, or in-memory computing, where we are going to move computation near or using the memory device themselves. If you are interested in a more detailed discussion on processing memory, I invite you to check our Pink Book chapter on the subject, which covers a lot of the research that we've been doing here in Safari. We are going to release a new version soonish, which is much longer than this one. So I recommend you to actually check the shortest one first, because it's going to be a lot of pages. And just as a reminder, we are classified these type of architectures, these memory-centric architectures, into two different sets. The first one is what we call process near memory, where we are going to just move the computation the way that we do right now with regular logic, closer and closer to the memory device itself. So we start by, for example, moving the computation from the core to the memory controller or near the caches. Then we enter the DRAM chip itself in the PCB or inside the DRAM, if a 3D stack system, in the logic layer of the DRAM device itself. And the closest that we get to the memory array itself, the largest is going to be the ability of exploit the memory throughput of those devices. The shorter is going to be the memory access time for accessing for access data for computation, and the more you're going to improve the energy saving that you can achieve. Of course, this comes to a cost related to fabrication and area costs, and the closest that you get to the memory array, the harder is for you to integrate logic as well. So there is this trade-off over there. So the alternative is what we call processing using memory, where over here is a complete paradigm shift. We are not going to add any logic for doing computation. We are going to use the analog principles, the operating principles of the memory device themselves for computation. We might add logic around the memory arrays for us to enable different types of computation, but still the primary means of doing the computation is going to be the operating principles of the memory device itself. So this is just a quick reminder of a summary of where the keynote left us. Does anyone has any question related to this classification of what you're going to talk next? Okay, feel free to raise your hand during the lecture if you have any questions. I don't see much from far away, so I'm going to try to do my best. So as I'm a PhD student from Onur Mutlu, I have a lot of things to cover and not enough time to cover them, but I'm going to try my best to cover all of the context. So I'm going to dive deeper in many of the subjects that Onur talk about, but please don't feel that you need to understand every single thing that I'm going to talk about in high level of detail, on fine-grained details, because it's going to be a lot of content. So I'm going to start with processing using memory architectures, and then I'm going to move into processing near memory architectures. Then I'm going to talk about, I'm going to elaborate on the barriers for adoption of this type of systems, and then I'm going to conclude. So before I talk about processing using memory, I need to give a brief background on DRAM so we can be on the same page on how the computation is going to be done, and it does not look like magic. Probably during the week, you have seen a similar set of slides like this many times, and you're already tired of hearing about activations and pre-charge, but I need to refresh your memory on all of those components. So a DRAM model is organized or is composed of several DRAM chips. Inside the DRAM chip, we have several DRAM banks, and a DRAM bank is composed of several 2D arrays of DRAM cells, which are called subarrays. So horizontal rows in a subarray shares a word line, and vertical columns are connected through bit lines. So the bit lines are connected to a differential sense amplifier, and a collection of this set of these sense amplifiers is what is called a row buffer. And in current DDR4 memory device, for example, we have around in the DRAM subarrays, around 65,000 of those sense amplifiers. So a DRAM cell itself is composed of a storage capacitor and an access transistor. So in order to access a DRAM cell, the memory controller is going to issue three main operations to the DRAM for the DRAM chip itself: activate, a read and write, and a pre-charge. So let's see how it works. So in the first step, when the memory controller issues the activate command to a particular row, this is going to raise the word line for that particular row address, which is going to connect the storage capacitor to the bit line. This is going to make the capacitor to lose charge to the bit line, generating a perturbation to its voltage level. Then the sense amplifier is enabled, and this perturbation is amplified to either VDD or ground, depending on the direction. After this perturbation is amplified, the data is restored to the DRAM cell itself, and the data of the entire column, the entire row, is latched to the sense amplifier or the row buffer. So after that, the memory controller can issue read and write comments to the data that is latched inside the sense amplifier. And when the memory controller needs to issue a follow-up a memory request to another row in the same DRAM bank, it needs to prepare that subarray for a follow-up access using a pre-charge command, which basically lower the word line, pre-charge the bit lines to its original reference voltage level, and disable the sense amplifier. By doing this type of computation, by access DRAM in this particular way. Prior works have shown that we can do much more than just accessing data. We can copy data across different DRAM rows without the intervention of the DRAM, for the processor itself. And we can also implement book bitwise operations like AND and OR. So just as a reminder, on already talk about this, prior works from our group called RowClone has shown that by issuing consecutive back-to-back activations to two DRAM rows in a DRAM subarray, this enables us to copy a source row to a destination row without the intervention of the processor itself. So this enables us to have significant savings in latency and also energy reduction. And the primary way of how this is operating is by the fact that the sense amplifier over here is is quite strong and can pull up the voltage that is latched from a previous activated row into another destination row that is further accessing the second activation request, allowing you to copy the data inside this DRAM subarray. So we also implement data movement across different DRAM banks inside the DRAM chip by using the share interconnect bus that is present over there. And basically what we do is we use the read and write command to copy the data from one DRAM bank to the other. This provides still some latency and energy savings, but since we are not operating inside the same DRAM bank anymore, the latencies and energy savings is not as large as if you are operating inside the same DRAM subarray. We also can move data across DRAM subarrays inside the same DRAM bank by issuing multiple of those inter-DRAM bank row copies. So all of this can be done with negligible area cost, so it's less than 0.01% of the area cost in current DRAM chips. And this enables us to improve energy and latency significantly compared to doing the same operation using the baseline CPU itself. So if you are interested on embedded, I invite you to check our paper and our lectures on the topic. So we follow up or we extend this also, I'm sorry, it was RowClone before. So we extended RowClone by enabling it to also move data in a more efficient way across, for example, different DRAM subarrays inside the same DRAM bank, and by doing other types of data movement primitives, for example, as data transposition using this figure proposal, also communicating across different DRAM banks using this norm. And later on, I'm going to talk about this embedded and SIMDRAM, which further is built on top of RowClone to implement book bitwise operations. So those are the reference for those works. I'm going to briefly mention the way that we can enable moving data more efficient across different DRAM subarrays inside the same DRAM bank using this LISA approach. So the main takeaway that we have here is that there is low connectivity across the different DRAM subarrays, which limits the throughput that we can do this processing these row copy operations inside the same DRAM bank. And we can fix that by simply interconnecting different DRAM subarrays using isolation transistors. So we use these isolation transistors to connect the sense amplifiers of neighboring DRAM subarrays together, and this enables us to copy the data the same way as we were doing before inside the DRAM subarray with these back-to-back activations from one subarray to another subarray, and improving performance compared to that other way that I mentioned before, which was using that internal interconnect inside the DRAM chip itself. So this is a work that we published in HPC 2016 called LISA. and we keep improve this substrate in follow-up works. Okay, so this was moving data inside the DRAM chip itself. So we are going to start building up on top of that and make this the computation capabilities of this processing using memory solutions more and more complex as we progress during this lecture. So we start really simple, moving data inside the DRAM array by using these back-to-back activate commands. And now we are going to enable proper computation by doing book bitwise operations. So and not operations inside the DRAM row itself at low cost. And the key idea here is quite similar to what we did for row clone, but instead of activating 2 DRAM rows at the same time, we are going to activate 3 DRAM rows at the same time. And this enables us to have quite large performance and energy improvement compared to doing these book bitwise operations inside the processor itself. And other memory technologies can also do the same thing. So Onur already mentioned this in this lecture, but assuming that we have 3 DRAM rows that you are interested in doing a book bitwise operation, so we have row A, B, and C, and all of those rows are connected, sharing the same bit line, connected to the same sense amplifier. So since this is a differential sense amplifier, when you activate the 3 rows at the same time, the 3 rows are going to simultaneously perturbate the voltage level of the bit line. And the sense amplifier is going to pull the voltage level to the majority of the voltage levels stored in the 3 DRAM cells involving the computation. So in this way, in this example here, the initial voltage levels were VDD, VDD, and ground. And because of that, when you activate the 3 rows at the same time, the sense amplifier is going to pull the voltage to the majority of that, which is VDD. So basically, we can think about the sense amplifier inside the DRAM subarray as a majority gate. And this is what we are going to be using in the follow-up works as well. In Ambit itself, they were interested on doing and OR and operations. So what they are going to do is they are going to restrict one of those rows that are involved in the computation, since if you want to do AND and OR using a majority gate, you can do so by setting one of the inputs to either 1 or to 0. And the Ambit proposal itself was first proposed in 2015, later on was published in the micro conference. So we can do, yes? Sure. Yes.
So what is the effect of the capacity? Bit line is a material, so it should have a capacity if you have very long bit line.
Yes.
So does the capacitive effect of the bit line and the sense amplifier affect the computation or adding errors to the computation or not?
It does. So this is not a bulletproof approach, because basically this sense amplifier here was not designed to drive 3 word lines at the same time, 3 cells at the same time. And we also have to, as you mentioned, we also have to take into account the capacitance of, or the impedance of this line over here, which is really long. So in other papers, we have shown the error rates that you can achieve depending on different manufacturing fabrication process, and but in most of the times we observe that you can achieve high accuracy by doing this type of computation. And there are techniques that you can employ to further improve this limitation of the fact that this word line, this sense amplifier here is not designed to drive 3 word lines at the same time. So there is this follow-up work that we did in actually commodity DRAM chips themselves, this same idea. And the idea over there to improve the success rate of this type of computation was to replicate the input several times. So if you replicate this 6 times in 6 rows here, so replicate it 2 times. If you do the math for the sense amplifier, you are back to the original sensing capabilities of the standard sense amplifier in the DRAM chip itself. And you can replicate it even further to further improve the success rate. Of course, this comes at the cost of storage. But it's one way of doing that and improve the computation reliability in current DRAM chips itself. And just a side note, another way of doing that we didn't try yet is to redesign the sense amplifier. So the sense amplifier is designed with the threshold have in mind for a single DRAM row cell, right? But we can rethink this amplifier design and design it with different thresholds and improve natively without this extra cost of replication the accuracy of the computation.
I have another simple question. So when you do the computation, so it's actually disturbing the values that already.
Yes.
You need to reprogram them again.
Yes.
The charges are like jumping from device to device, so it means kind of we lost the information. Yeah. We
lost the data. So this is the destructive computation, and this is a really important point actually, which we are going to take into account into the next work. So just bear with me a little bit, but we are going to get there. Any other question? Okay, great. Thank you so much. So where I was? Okay, so now we can do data movement operations. We can do AND and OR. And for us to be functional complete, we are just missing NOT, because if you have NOT, you can implement AND and OR, and then this is a functional complete. And the main idea that we are going to use here is that the fact that this is amplifier here is actually 2 back-to-back inverters connected in a loop. So we are going to redirect. So we already have a NOT implemented inside the DRAM chip itself natively. So we are going to redirect one of the outputs of these amplifiers back to the DRAM cells using these dual contact cells over here, this transistor, and this allows us to have the negated version of one of the inputs as needed. So now we can do AND or NOT and copy operations as well. And this is just explanation on how this works. So with that, we have implemented in this empty paper NOT and NAND and XOR operations, and we see a significant improvement in performance in terms of throughput and energy compared to a baseline CPU system. So in the embedded paper, we use these book bitwise operations to accelerate some key applications like bitmap index using in databases. So, for example, if you have a database and you want to filter the age, or is a query that we have to filter the age of people, we can implement that using bitwise operations across bitmaps. So we implement that and you compare again to a baseline CPU system, and you see 5 to 6 times performance improvement compared to that. Another database operation or database application that uses big bitwise operations is what's called bit weaving. And I'm not going to get into details on how it's implemented over here, but again, if you implement this application using this substrate, we can have 4 to 12 times performance improvement, depending on the number of bits that you are going to compute. So all of that is in the embedded paper. So I'm referencing the papers here just in case later on if you want to check all of them. And later on I'm going to move to doing more fancy things with this substrate. So as a recap, we started with row clone, and then we did data movement operations inside the DRAM array without any logic for that. Then now we can do Boolean bitwise operations. We can do AND, OR, and NOT, and this enables us to have a functional complete substrate. But the question now is, can I do addition or can I do subtraction? Can I do something that my real application is actually going to use in a high-level C programming language, for example. And the question is, yes, by composing this book bitwise operations or these Boolean operations, we can implement more complex arithmetic operations using the same ideas of row copy and in-DRAM majority operations. And this is the work that I led called SIM-DRAM. And basically, SIM-DRAM is a framework designed to allow the user to input the operation that the user wants, and the system itself gives the substrate and the system support to support that given operation. So it enables the user to implement arbitrary complex operations inside the DRAM chip itself. And at the same time, it enables us to start looking at DRAM now not only as a memory substrate, but also as a massive parallel SIMD substrate, where each one of those DRAM columns that I mentioned earlier, those 65,000 in DDR4 devices, can now be seen as a SIMD lane of in a vector processor. And all of that with minimal change to the DRAM architecture itself. So the main idea or the main feature that we are going to leverage in the SIM-DRAM substrate to enable that in DRAM is first the idea of using a vertical data layout to represent data. So if you want to do addition, for example, in DRAM using embedded substrate, so you're using AND and OR and NOT gates, you can think about RIP carry adder circuit, right? Where the majority of the gates over there is composed of is actually XOR gates or AND and OR gates, right? The problem is that if you want to do a high precision computation, let's say 4 bits and addition or 16 or 32-bit addition, at some point you are going to have to start propagating the carry in that heap carry adder circuit. And if you remember the DRAM organization slides where I mentioned before, let me just find a good example here. So if you go back to how the DRAM is organized, so the data is going to be usually in conventional system is stored horizontally here, right? So we have all of those columns, and then you're going, if you have the 16 bits of data, you're going to place the 16 input data in one row, and let's say the other 16 for the other operands in the other row, and then you do the computation. But when you have to propagate the carry generated for these first bits to the other one, you don't have a way to do so because there is no interconnection across the different DRAM colors inside a DRAM subarray itself. And implementing some network to connect all of those different DRAM columns inside the DRAM subarray is quite costly because, again, recall that over here we have, so this is 4K for DDR3, for DDR4 is 8K, so 65,000 of those columns. So this network will be quite costly to implement. So instead of implementing such a network to enable us to propagate carry doing arithmetic operations, we are going to transpose the data in on the fly. So every time that we have a piece of data that you want to do, processing using DRAM computation, we are not going to store it in the DRAM subarray using this horizontal data layout that spans the words across the different DRAM columns. Instead, we are going to place the data vertically across the different DRAM rows. And what this enables us to do is now the pieces of data from involving a particular operation are stacked together, and now they share a communication path over here. They share the column, and now I can simply propagate a carry operation generated by adding this bit to this bit by by doing a copy operation from one of the other rows to the other rows. This is going to enable us to implement this implicit bit shifting operation, which is the primary operation that you do when you are propagating carry data through arithmetic operations. And at the same time, now we can see these columns as SIMD lanes, right? Because each one of those columns are doing, for example, addition operation or a multiplication operation. Similar to how different vector lanes operate in vector processors in the CPU system. So another thing that we are going to do is fully leverage majority-based computation. So in Embeds, if you recall, we are setting one of the inputs of the operation to either 1 or 0 to implement AND and OR. And we can use AND and OR and not to do the majority of the computations, but in most of the cases, this is going to lead to more triple row activations required to do a given computation. But we can just use a majority-based logic similar to regular Boolean logic, since our simplifier, which is our primary agent to do computation, is basically a majority gate. So compared to doing computation using AND and OR or not operations, we can have higher performance because we can reduce the number of triple row activations required for a given computation, and also higher throughput. So with those two things together, we implement this SIM-DRAM substrate, which is composed of 3 main steps or 3 main components. So the 2 of those components are offline components, so the user does do it once, and it can be reused for follow-up tasks. And another component is a runtime component, which is going to be responsible for dispatching instructions. So the first step, so the user inputs as to the framework, a representation in terms of logic gates of the operation that needs to be done. So repair carry adder circuit, for example, or the circuit for the add and shift circuit for multiplication, or the equivalent one for division, for example. And the first step is going to be to translate this circuit, which is represented using AND and or not majority gates, into only a circuit with majority and not gates itself. The second step is responsible to translating this circuit representing using majority gates into a sequence of row clone and embed operations, so in-DRAM row copies or in-DRAM majority operations that can represent that circuitry inside the DRAM array itself. And the output of those 2 steps is first what we call a microprogram, so which is the sequence of in-DRAM row copies and majority operations for that particular computation, and a new instruction that the processor or the programmer or the compiler is going to use to trigger the execution of that operation in DRAM itself. And during the execution time, we have extension of the memory controller, which is responsible for fetching that sequence of instructions of in-DRAM row copies and in-DRAM majority operations, and dispatch that to the DRAM chip itself. So I'm going to briefly elaborate on how all of those steps are going to work. So as I mentioned many times already, you can represent, there is an equivalence between AND gates and OR gates to a majority gate. So you can, if you have, this is a circuit, if I'm not mistaken, to generate the carry out of a carry adder. So if I have this circuit, I can implement it in Embed as it is by simply replacing the gates over here with majority gates following this equivalence. But this is not efficient, because the circuit can be further optimized using majority-based logic, and similar to what we will do we're using regular reduction rules, like the Morgan, for example, using in your Boolean circuit. So instead of doing that, we are going to first convert the circuits to its naive majority-based representation, and we are going to use some EDA tools, some optimizers that targets circuits implemented using majority computation, majority gates itself, so that we can eliminate some of those gates. So in this case, for example, we can reduce the circuit from 4 majority gates into 1 single majority gate. And this means that instead of having to issue 4 times sequence of triple row activations to DRAM, I only need to issue one. So the latency is quite reduced. So the first step in the SimDRAM framework is going to generate this optimized majority knot implementation of the desired operation. So the second step is now responsible to translate this efficient or optimized majority knot gate into a sequence of optimized in-DRAM row copies or in-DRAM majority operations. And we call this sequence of operations a microprogram. So this step is further broke down into two tasks. The first one is we need to map the inputs of those of that circuitry, that majority knot circuit, into DRAM rows to prepare the computation, and later on we need to generalize this microprogram to be able to implement n-bit computation, because the circuit is only for 1 bit, right? So if you want to have to do it many times, you need to generalize it to that n-bit precision that you need to do the computation. So the first step, this allocating of DRAM row operands, is going to take two constraints specific for processing using DRAM. The first one was already, the first one is that in the Mbit, I didn't mention this before, but in Mbit, we are going to have this specialized row decoder inside the DRAM subarray itself, which enable us to activate 3 DRAM rows with a single DRAM address. So this is the only function of this row decoder, so that we don't have to issue 3 consecutive back-to-back activations to DRAM. So it's just to facilitate or reduce a little bit the latency of the computation. Again, just as a highlight, this is not fundamental for the computation to be able to work. It's just optimization. But if you employ this optimization, this means that we're only going to have some few rows inside the DRAM subarray connected to this special row decoder. So we have to take this into considerations when mapping the initial circuitry. The second one, which was mentioned before, is that when you do a processing using DRAM operation, this is going to destruct the initial input data that you have stored in the DRAM rows itself. So the data, if you activate 3 rows at the same time, at the end of the operation, the 3 rows are going to have the output of that majority gate implementation. So you lost the data, basically. So you also need to take into account. So the way that we are going to do this mapping then is quite trivial, actually, but we are going to do some optimizations on the way. So the first thing that we are going to do is that we are going to go through every single one of those edges of this circuitry here, or every single of those inputs, because those represent input rows that we need to have inside the DRAM substrate itself. So we are going to allocate every single of those inputs as input rows inside the DRAM array itself. So the second step, so this step is going to take into account the structural behavior of the triple row activation itself. So if over here I only have one example, but imagine that this majority gates, there are other majority gates connected to the output of this one here, right? So when I do this triple row activation, I have the ability of, after the computation, I'm going to have the 3 rows. We are going to have the 3 copies of this edge inside my compute rows over here. So if other circuits need to use this output, I can directly access them through each one of those 3 rows without having to copy the data beforehand. So they can be reused for further allocations. So the next step, once I figure out my addresses of the places that the rows are placed inside the DRAM array itself, I need to start generating computation or in DRAM row copies or in DRAM majority operations to create the sequence of operations that implements that computation inside the DRAM array itself. So the first step is basically going to go through each one of those input rows and generate row copy operations to some reserve space inside the diorama array. And this is trying to mitigate the problem that the data is destructive. So basically, I'm copying the input data to some temporary rows inside the diorama subarray itself before I destruct those rows. And then I destruct the rows by issuing the majority operation over here. And in the end, I copy the output of the majority operation back to a reserve row to store the output itself. So this gives us an initial microprogram that works, but it still is inefficient. And I can further optimize this microprogram by coalescing some of those row copies, by leverage that some special properties of that row decoder that I mentioned before that can activate 3 DRAM rows at the same time. So here I can issue with a single activation, I can activate all of those 3 DRAM rows at once. And I can also merge some majority operation followed by activation, because if you think about this, this is basically activate followed by other 2 activations. And then this gives us triple activation. So the same thing that special row decoder is doing. So by doing that, I can further optimize or reduces the number of in-DRAM operations that I need to do, further improve latency. And now the only thing that is missing is generalize the computation to a n-bit computation, because this is only executing a 1-bit operation. So I basically need to make sure that I repeat this n times, and n meaning the target bit precision that you have for that particular computation. So this gives us the final microprogram, which is stored in a portions of the DRAM space for future use, and a new instruction is added to the CPU ISA so that the processor can trigger these operations over here. Is there any question on those steps? Just.
So you put the A, B, and C.
Yes. 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 So it does, it repeats for all of the bits.
But we need the C out of the first bit to go to C.
Yes, and the C out of that bit is in the, is already in a node, because I transpose the data, right? So the C out, so I don't know, this is storing my first bit, this is storing, let's say that I have two bits for computation. So these the first 2 here is storing the bit 0, this stores bit 1, and then I have B here, bit 0, bit 1, then my output. So I'm going to activate this first one, these others, like say row 0 and row 2, and then I'm going to have the carry of that particular bit here. Stored in this column. And then for the next bit, it's the same operation, but now I'm going to activate this row indexed 1 here, together with the row indexed 3, plus that carry that was generating the previous step. So activate the 3 of them for generating bits 2, plus the carry for the third carry, right? Because it's 2 bits in this case.
And the second question is about the read and write. So we did read. So during a read, you...
I think it's turned off. Maybe we ran out of charge. Anyway, I can repeat the question.
During the read operation, you activate 3 rows.
Yes.
But during the write, you activate only 1 row, right?
So...
The 3 of them, you are going to write the same data.
So when you activate 3, we both read and write, because it's how the process is, because the process is destructive, right? And the rows are all, the 3 of them are open at the same time. So I didn't show a diagram of how this works in DRAM, but basically you can think of this over time. So you activate the 2 rows, they are read, they are activated. I kept the word line high for all of those 3 rows. And after some time, my system amplifier is going to do the majority operation, and it's going, because everything is connected to the bit line, is going to drive the data back to the cells. So you don't need to issue a read follow up by a write. Everything is encapsulated in the same activation command.
I meant the read before doing the computations, because you are putting A.
Ah, the copies.
Yeah.
Yeah, yes. So what is the, sorry, didn't get the question for those?
So the decoder is not the same, right? For the read, for the write A, B, and C in, and for the computation, the decoder differs.
The decoder, yes, the addresses are different. Yes, and this is why, like, this is what that microprogramming generation is figuring out, actually, is the addresses of those rows that should be activated or read and read during a particular time, so that in the end you get the computation.
Okay, thank you.
Welcome. Another question? I think I thought another hand. Okay, maybe there is no another question. Okay, so with all of this, what is left to do is now control this. So again, this is an offline step. So every time that you have, you want to do a new operation, let's say that you want to do FFT now, you input the FFT circuit to the framework, and then in the end, the framework is going to give you this sequence of operations and the new instruction. But now you can just reuse that instruction as many times as you want. So you can create a pool of regular instructions or useful instructions that are going to be used for many applications. And this is what we do in this work. We generated 16 different operations like addition, subtraction, multiplication, division, ReLU, bit count, bit pop, all of those type of things. And we just later on map applications to those instructions. So the third step is just a simple control unit that is placed inside the memory controller that is going to be responsible for, once this instruction is encountered, fetch that sequence of DRAM operations to do that particular computation and issue the operations in order to the DRAM chip itself so that the computation is performed as needed. So in the very end, you have the instruction result in memory without much intervention of the CPU. So for all of this to work in a system, many things need to happen. So we need to find a way to, so the first problem, right? Originally the data is horizontally placed. Now I'm asking you to transpose this data, for example. You also need to have a programmer interface so that I can go from my application using that new instruction and trigger my hardware device. I need to handle many system problems. So what would happen if I have a page fault? How I deal with address translation from a virtual address to a physical address placed in DRAM? If portions of my data is in the caches before doing the computation, how I handle coherence or interrupts. So my subarrays have limited sizes. So how I deal with spill-offs across subarrays. There are some security implications and some limitations. So in the paper, we talk about all of those problems. But over here, I'm going to just mention one of them, which is the transposing problem itself. So if your application, so I'm not going to ask you to transpose every single time that all of the data, independently if it's going to be executed in DRAM or not, because this is going to create performance problems for the system. There is a reason why we organize data horizontally in current DRAM chips. And so this is to improve the throughput and utilization of the multiple channels and banks and chips that you have inside the subsystem itself. So transposing all of the data would create a performance loss for applications that are not processing using memory friendly. So I need to find a way to efficiently transpose every time that I'm going to do a process using DRAM computation, transpose the data and from this horizontal to vertical and vertical to horizontally, hopefully transparently from the CPU. And to do that, we basically devised this transposition unit that is sitting between the last level cache and the memory controller, which is basically going to first track only the memory addresses or the memory objects that are going to be used for processing using memory operations. And when those memory objects are encountered, it transposes in hardware the data and store it in DRAM in the transpose manner. And once the CPU requests back that data, because probably later on in your application you might use that computation, it transposes the data back from this vertical to the horizontal data layout. This transposition unit have really is a small area cost in terms of area of the processor itself. So we implement 16 different operations using the substrate, and we evaluate those operations compared to a CPU, a GPU, and doing these operations in the ambit way. So using and, or, and not operations instead of using majority logic itself. So we see that, and we also evaluate SimDRAM using multiple DRAM banks for computation. So the more DRAM banks, the more parallelism that you're going to have and to exploit for processing using DRAM computation. And so compared to the CPU, SimDRAM with 16 banks achieve 80 times normalized throughput. This is normalized across, average across all of those 16 different DRAM operations that I mentioned. Compared to the GPU, we can have up to 5.8 times the throughput for if you use 16 DRAM banks, and compared to ambit, we improve the throughput for by 31.6 times. So we also evaluate energy. So this is performance per watt. And compared to the CPU, GPU, and ambit, SimDRAM significantly improve energy efficiency. And with basic, and after that, we take those 16 in DRAM operations like addition, multiplication, all of those, and we find 7 real-world applications, or didn't find. We look at 7 real-world applications which are memory bound, and we manually modify them to use this substrate, to use those new device operations in DRAM. And we see that by doing so, we can significantly outperform the CPU, the GPU, and ambit in all of the cases. So SimDRAM is an efficiently and effective solution for real-world applications themselves. So this concludes the SimDRAM part. In the paper, have much more discussions on other things. And if you are interested in a more elaborated discussion, I invite you to check this lecture that we have online. So just to summarize before I ask for questions, now we left by, we started by enabling something really simple, which was copy operations in DRAM. We moved to Boolean operations like and, or, and not operations. And now we are in the, we add a little bit more complexity, and now we can do fancier things like addition, subtraction, multiplication, all of that natively in DRAM without adding logic gates specifically to do that particular computation. We are going to make it more complex next, but before I'm going to see if there is any question. Sure?
I'm just wondering, maybe one of the problems to identify about how to undo data arrays.
How to get, sorry, I couldn't.
How to undo data arrays when you have programs having to have you thought about,
I think
about some of the problems? I know you talk about that it's a problem about memory coherence.
Yes.
But one related problem I see is data arrays when you have programs having to contest for access to, because you are doing addition.
Yes.
So you may have several different programs trying to add and store you have the same memory.
I see. So yeah, that is definitely a problem of memory ordering. So there is one good thing about DRAM. DRAM is really large and is really parallel in nature. So you can reorder the request. Of course, if at any given moment in time you are contenting for 2 memory requests, one for computation, the other one a proper memory request, to a single bank, this is going to create a conflict. But this would create a conflict regardless, even if the memory is trying to access, if you're not doing computation in the other data, but you're still going to access the data, and you have 2 requests to the same bank, this would also create a conflict to that particular bank. So that bank conflict would happen regardless. The only difference is that now I'm adding a little bit extra latency for the conflict because I need a little bit more time to do that addition, for example. But in the meantime, meantime, the memory, if I have a memory controller that is aware of that, I can schedule other memory requests to other banks which are idle doing nothing, or I can, from the go, I can initially partition my banks in a way where some of my banks for a period of time are going to be dedicated for the computation, and some of the other banks are going to be dedicated to serving the memory itself. And when I allocate data, I allocate in a way where the data that I know that is going to be useful for process using memory, I allocate these banks that are dedicated for computation, and the other ones I allocate for regular applications data itself. So I'm basically creating a partitioning in that point of that allocation, and that is possible. I don't know of any work that address that. Is a problem itself, but there are ways of if you have a smart enough allocator and memory controller, you can minimize or mitigate that latency conflicts as much as possible. So hopefully. Sure. I think this one is dead. Maybe we need to get this one. But you can, I can try to hear from here.
So now you can do these operations inside of DRAM. My question is, if you have, for example, a multiplication in a program, how do you decide whether do you do it like inside DRAM or do you bring data to CPU? Do you always do it in DRAM or these are the cases?
That's an excellent question, and there is no good answer for that. So there is the latency of doing the computation, portions of the latency of doing the computation in DRAM is fixed. So it depends, giving a precision, I always know how many activations I'm going to need to do the computation. So I always know the portions of the latency itself. But there is a component of the latency that I don't know until I run the application, which is how much of the data is in the cache, how much of the data is in DRAM, how much of the data that after that computation is going to need to be bring into the cache, or how much of the data is going to be stay in DRAM. So this is a dynamic problem in nature, and there are still really few works that addresses this problem of like doing the execution time, figuring out a given operation if I should offload it to DRAM or if I should keep in the CPU itself. Is an open research question right now. What we're doing in these works is that we know for a fact that the applications that we are using are memory bound because we profiled them before. So we know that a multiplication in the memory bound phase is going to always face cache misses because of the data is mostly in DRAM the majority of the time. So this is why we just offload over there. But in a more realistic way, you don't have that profiling given to you before, right? So you need to actually doing the execution, figure it out by itself.
I see, but in the case, if all the data is stored in DRAM, it's always good to do there, right?
If the data is always stored in DRAM and is going to stay in DRAM from future use, or only really small portions of the data is going to ever leave DRAM, is better to do it over there in the DRAM itself for both performance and energy sake.
Okay, thank you.
I remember from the keynote that there was a comment on the majority gates being somewhat error prone, right?
Yes.
Do you know where these errors come from or what could be improved to mitigate those problems?
Yeah, we know. I'm not going to talk about majority gates in general, but like in majority gates implemented in the way that we are doing over here using the sense amplifiers. The problem is that the sense amplifier was not designed to be strong enough to activate 3 rows at the same time or to sense three perturbations to the bit line simultaneously. At the same time, we have other sources of variation, process variation, and for example, the capacitance of the bit line for different DRAM subarrays. So all of that are things that are if you don't take in DRAM computing into account, and at the same time you try to do that, is going to lead to an unknown behavior of the circuitry. So the majority of the problems comes from there, like the circuit's not designed to do that. You can design the circuit is not designed to do that, meaning it's not designed for multiple row activations, it's only designed for one. But you can design larger sense amplifiers, which in principle would be able to activate as during the design time as many rows you define, and but still you would have the variation process that is inherent of this type of analog processing, and that is just coming from fabrication itself or reduction of transistor size. And in the SimDuran paper, we actually have some SPICE model that we do to see like, oh, as reduce the node size and doing computation in these triple row activations, or we even check 5 row activations, how this process variation impacts the success rate of the computation. So I think I hopefully answered the question more or less.
Yes, thank you.
You're welcome. Sure, there are one there, one under there.
I have a slightly higher level question.
Sure.
When you're computing in DRAM, I'm assuming the CPU is idle at that time. So you're pushing a bubble, and in case you have a peripheral which was requesting this data, then does it not still take the same amount of time to come back to the processor and then go through the fabric and then to your peripheral?
So it does not take, it takes less time in principle, because you can think about this as if I don't do this process using DRAM, my CPU is going to sit idle because I'm going to have a cache miss, and like the latency of a cache miss is quite high, especially if you go off chip. So you go off chip, you read the data, and recall that the size of the bus that you can transmit data is much smaller than the granularity of the row itself. So if you need to bring all of these, I don't know, 8 kilobytes of data, you need to move them at granularity of 64 bits, for example. So it's going to take a lot of time. Then you need to populate the caches. Then you need to do the computation. So there are all of these components of this latency. While if I do this computation, I don't have this component of hopefully I'm going to do many operations over there in the DRAM. And then I'm going to later on just move the end operation. So if I do a sequence of operations, and I just move the very output of that. So hopefully the data is smaller, this the granularity. And if you do the math, the latency of doing this in a book way, this is why the book word is important over there, is smaller than the latency of doing the same book operation in the CPU itself, assuming that the data is sitting in the DRAM. So for the takeaway that I want to give is that for a single, if you are not operating in a book granularity, yes, it's pretty likely that bringing the data to the processor is going to be faster. But once you're operating large amounts of data, this is more efficient in terms of latency because of this movement of data through small channels.
Okay, I have a small follow-up question to that.
Sure.
You mentioned 35x energy improvements and all of that. Did that consider the CPU being idle, the energy savings from that? Or was it like power gated? Or
it's not power gated, but we take into account the static energy of the processor sitting doing that at that time.
So you can really improve that energy saving further by sort of.
I don't know the name. I don't remember the number from the top of my head, but that number compared to the saving that you get from not bringing that amount of data through the memory channel is actually really small, because that memory channel is really power hungry, even compared to the processor, even if you don't power gate, for example. So I don't remember the breakdown from the top of my head, but it's a lot more moving the data through that channel.
Thanks.
I think there was another question.
Sorry, I have another question, which is kind of follow-up.
Sure.
In terms of parallelism, so say I want to do a lot of additions or multiplications, and they can all be done in parallel, so they're not dependent. what is the limitation of doing that inside of DRAM?
So the number of, there are some limitations. The first one is the size of because there is a physical size space, storage space inside the DRAM subarray or the DRAM bank, right? So if you want to just like do all of them in parallel at once, that is going to be your first limiter. So as a subarray, our DRAM bank, if I'm not mistaken, store something like 16 megabytes of data. So you can do as much as that in parallel. So this is one, but of course, you can repeat that many, many times, and you have several of those DRAM banks, and so you can replicate them across those banks. But at some point, you reach the maximum of storage that for that particular DRAM bank or DRAM model itself. The good thing about DRAM is that DRAM is really scalable, or is designed to be really scalable, right? So if you end up running out of capacity for that particular organization, you can always duplicate across ranks or duplicate across channels, and we have some scalability analysis in our papers, and we show that it scales almost linear with the computation. The throughput scales almost as linear, depending on how much more you put into the system in terms of parallel structures. So this is not going to be so much true in the next work that I'm going to talk about, because now we are going to share some resources for some computation. So, but if it's like just embarrassing parallel, this is just a great substrate for that.
Thank you.
It's just a small comment, not a question. So you mentioned that when you increase the width to increase the capability for the sense amplifier to read 3 rows, this is not only going to increase the capability, but it's also going to decrease the variability on the sense amplifier itself.
Yes.
Based on the parallelism model.
Yeah.
And the second thing is that's going if you decrease the variability on the sense amplifier, it's going to make the operation even faster. Because if you decrease the variability of the sense amplifier, you can read even faster. So it's going to solve not only one problem, which is the problem of the capability, but it's also going to increase the read speed, and it's going to decrease the variability inside the sense amplifier itself.
So if you isolate I think Girai some days ago talked about some isolation, breaking that DRAM subarray into 2, right? So you're already breaking down it over here for computation and for storing the data, but you are not cutting the bit line short. You are keeping it at the same length. But if you actually do that, then actually I can design a sense amplifier that's fast, or the amplifier would perform faster because the capacity of the bit line will be smaller, and I can design a sense amplifier that would operate faster because the length of that line is smaller. So yes, I can do this type of optimizations if I understood correctly.
My point is, if you make it larger, it's going to be faster.
Yes.
So by itself, without doing any modification, by just changing the sense amplifier.
And make it larger.
If you make it larger for more capacity,
yes,
tell 3 rows, it's going to be faster, first of all. And the second point is that it's going to be also to suffer less for the variability. So you have more swing.
Yes.
And much faster also. So it solves 3 problems in one.
Yes, but at the cost of a very large sense amplifier. And I think, I guess Onur mentioned before, this is actually the main bottleneck in the DRAM array itself, actually. Like the cell is much more smaller than the sense amplifier design. And of course, I'm not saying that we shouldn't do that. I'm prone to think that this enables a new type of product line. So where if you can make that efficient, you can have a DRAM that is now going to be sold as an accelerator, so that you can pay this trade-off. So doesn't matter if your density is going to decrease a little bit, because your primary target is not to sell gigabytes per bit, right? Gigabytes per dollar is to improve computation. So I think that's a really feasible trade-off to make, actually.
Okay, thank you.
Okay, so I'm going to try to finish up on time. So I'm going to move on to the follow-ups. So all of this is nice, is great. I can do copy, I can do book bitwise operations, and I can do complex arithmetic operations in DRAM, right? But still there are several limitations on this type of substrate. For example, I'm always operating at fixed granularities, right? I'm always operating over the amount of data that fits in a DRAM row. So 65,000 elements at once. So the first question is, does real applications have that amount of parallelism available over there or not? Or people usually write codes in a way or operates on tends to operate in smaller amount of data at a time, many times. Or another problem is this data layout conversion from this horizontal to this vertical data layout. So I didn't highlight much here, but when I'm doing this type of operations, I'm changing the paradigm. So when I do computation on horizontal data, I'm doing operations in a bit parallel manner, right? So the latency does not necessarily depend on the bit precision. Of course, it depends on, this is going to create some delay on the circuitry, but it does not necessarily scale with the bit precision of the computation. Over here, I'm doing a computation bit by bit in a bit serial manner. So it means that doing a 16-bit addition is going to take twice the same amount, the same time than doing 8-bit addition. And this gets worse because if I do multiplication, multiplication is an operation that scales quadratically with the bit precision. So doing a 16-bit multiplication takes 4 times more latency than doing a 8-bit multiplication, for example. Another problem is that I mentioned that we have this new ISA instruction for computation, but I have to go manually and change my application to make use of those, and this limits my application scope. So we are still improving one step at a time, but I'm going to mention in more detail how we address at least 2 of those issues in this work that I published this year in HPCA. So in this work, we are addressing 3 main limitations of this SIMD-RAM type of substrate. The first one is that since the granularity of computation is fixed to those 65,000 operations per time, when you go to real applications and try to map those real applications into substrate, a lot of time you're going to have SIMD underutilization. So it's really rare that you actually have across the entire run of the application, that amount of parallelism so that you can have high SIMD utilization from your substrate. And even if you have high SIMD utilization, it means that for you to have if you have the amount of parallelism, for you to have high SIMD utilization, you need to have exact multiples of 65,000 data per element so that you can compute at a time. Otherwise, you're going to end up in some sort of SIMD utilization. This is going to lead to throughput and energy waste for your application. The second one, I mentioned that we can do all of those operations, right? Addition, multiplication, but I cannot do something like reduction. So if all of those operations are in parallel, meaning that I'm taking a vector, I'm operating addition, for example, on top of this another vector, and I'm producing a third vector of the same size. So if I want to do, if I have a vector and I want to reduce that vector into a scalar operand, for example, I cannot do that because I don't have connections across the different DRAM columns storing the different elements. So I cannot do reduction, for example. And the third step is this challenging programming model, because basically this is a new substrate. You don't have a compiler that is designed to map computation to this subsystem. So the problem that we are trying to solve over here is that this large and rigid granularity of process using DRAM operations is limiting its applicability to a large set of applications and also its efficiency. So our goal over here was to design a process using DRAM system that overcome these 3 limitations. So I'm going to give a little bit more background on on DRAM and explain a concept that is called this fine-grained DRAM access. So I mentioned many times this DRAM structure, right? The DRAM subarray, but a DRAM subarray in practice is further divided into what is called a DRAM mat. And every one of those DRAM mats are usually around 512 to 512 columns and rows. And when you do a DRAM access, let's say that you want to access these columns over here, the word line is going to propagate across all of the DRAM rows, and it's going to activate every single of those rows across the different DRAM mats and bring the data to the sense amplifier itself. Even if you want to access only portions of the data that is not going to that's already placed in, is not necessarily, so it's placing on some mats, but not placing another mats. So this is a known problem in DRAM subsystems. This is not specific for processing using DRAM. And prior works have tried to mitigate this problem that often leads to throughput waste, but also energy waste, because we are now activating rows that are not going to be accessed. And by segmenting this global word line in a fine-grained manner. So the main idea here is that when I access a DRAM row, I segment this global word line. So I disconnect the global word line going through all of the DRAM mats. And I only enable the connections from the global word line to the mats that I'm going to access themselves. And this is a really old idea. People have been using this to improve energy efficiency in many different systems. And as I mentioned, this is called fine-grained DRAM access, because I'm deciding which one of those mats to access depending on the data that I'm going to further later on read. So the key idea of MIM DRAM is to employ or to leverage this fine-grained DRAM activation for processing using DRAM computation. So what I'm going to do over here is that I'm going to segment the word lines, the same as before, mentioned before, and I'm only going to issue triple row activations to the mats that have proper data. So I'm going to match the granularity of my computation. So let's say that you have 32,000 elements. I'm going to activate only half of my mats inside my DRAM subarray so that I can save the energy of activating the unused mats. So for a single process using DRAM operation, I'm going to only access the data of the mats with the target data. And this enables another thing. So if I have an operation sitting in the half of my mats, and I have a data-independent operation sitting in the other half of the mats, I can do these two operations in parallel now. So for multiple processes using DRAM operations, I can execute them independently across the different and concurrently across the different DRAM mats inside a single DRAM subarray. So I'm moving my execution paradigm. So in SIM-DRAM, I was executing in a SIMD manner because of this data placed across the different columns, right? Now I'm going to execute on top of that, in a multiple instruction, multiple data manner. So a MIMD manner, this is where the name comes from, where I have multiple instructions, multiple processes using DRAM instructions, executing across the different DRAM mats. So the third thing that this enables is that the mats, they share this data path across global system amplifier, and I can use this shared path to move data from one mat to another mat. And this enables not only this sharing of data, but the implementation of more complex operations like reduction, because I can do, let's say, if I do a vector addition now, I can implement my vector reduction as a reduction tree. So the first step, I do the addition in all of those mats. In the next step, I move the data from half of the mats to the other half of the mats. I disable that first half of the mats. Then I implement the next reduction step. Then I go so on and so forth until I have the data sitting only in one mat. So now I can further do reduction operation. And another thing that this gives is a nice property, because as I mentioned before, these mats usually have 512 rows and 512 columns. It just turns out that this is also the number of SIMD lanes that you have in vector ISAs. Like if you have AVX512s in your Intel processors. This 512 means that you have 512 lanes, which is exactly the number of lanes that you have over here. So I can reuse vector compilers to generate code not only for processor-based vector engines, but also this processing using DRAM substrate. So we are going to use all of these ideas to design this hardware software process using DRAM system that is going to leverage fine-grained DRAM for low cost and low programmability effort process using DRAM substrate. And process using DRAM is composed, as I mentioned, as portions of hardware and portions of software. So I'm going to briefly talk about the hardware part. So the first part that we have on the hardware side is some simple modifications to the DRAM access circuitry to first isolate those different DRAM METs using some isolation transistors and some MET selectors, select the METs that I want, and some further interconnect for me to allow to move the data from one MET to another MET to that share communication path that I mentioned before, this global simplifier. We're also going to extend that SIMDRAM control unit to now being able to map and control different different process using DRAM instructions. So I can have, since I can have multiple different DRAM instructions executing across the different DRAM METs, I need multiple of those microprogram processing engines that I mentioned before. You can see these as copies of this control unit that I mentioned for SIMDRAM, and somehow some way of figure out which METs are being used during a particular execution time. So on the software side, we implement some LLVM-based compiler passes to identify code that can be mapped to the substrate using the compiler auto-vectorization loop, schedule and map data-independent operations inside that loop to different DRAM METs, depending on the granularity of the computation, and also finally generates the process using DRAM operations and embedded those operations in the binary of the application itself in a way that is transparent from the user. So really briefly, I'm going to talk about the compiler support. So this is implemented, as I mentioned, passes in the LLVM substrate. And the first pass is basically an extension of the already present loop auto-vectorization engine, which is going to try to find vectors loops in the application itself. We are going to do some modifications to the auto-vectorization engine because we now want to vectorize these loops to their maximum number of parallel instructions that they can do in parallel, because we don't need to vectorize them to fixed 512 AVX instructions now, right? We can vectorize them to varying granularities of different MET sizes, depending on the data parallelism present in the loop itself. So the second pass is responsible for code scaling and data mapping, and this is going to basically generate a data dependence graph of the vectorized loops, and going to traverse this data dependence graph to figure out which operation should be executed in which METs. So operations that are dependent, they need to be executed in the same MET so that I don't keep moving data across the DRAM subarray. And operations that are independent, they can be executed across different DRAM METs concurrently, so I can save latency. And finally, the third step is the extension of the 886 backend, where I'm going to encapsulate the process using DRAM instructions that are equivalent to the operations that I need to execute in the DRAM, together with some metadata to control the METs. We have much more system support implemented in SIMDRAM. This paper is quite dense, actually. And over there, we deal with things like data allocation, alignment, add-on translation, and data coherence, and more other system integration things. Briefly on the evaluation. So now we took 12 applications from different benchmark suites. So this is like Polybench, you have SPEC, this is not parsec, Phoenix benchmark suite. So those are like real applications, and we we compile those applications using our new compiler, and then you map them to this MIM-DRAM substrate. So compared to the CPU, GPU, and SIM-DRAM significantly improve performance per watt for those three systems. And you also evaluate the case where you can have multiple applications executing in a single DRAM subarray versus using the same application executing across different DRAM banks and in SIM-DRAM, and we see that in using a single DRAM subarray, MIM-DRAM or single DRAM bank, MIM-DRAM can significantly outperform SIM-DRAM for those applications. So we have way more analysis in the paper, like comparison using subarray and bank level parallelism, comparison to prior process using DRAM systems, SIM-DRAM SIM utilization versus SIM-DRAM, and area analysis. So all of that is in the paper. So is there any question related to MIM-DRAM? Yes. Which microphone is the one that was working? It's not this one, right? Ah, it's that one.
Format or para which do reactive refreshing, then how does the latency increase for in-memory compute? Because is it still going to be lesser than having to bring it to the core and then compute and then send it back?
So I think, if I answer correctly, you're asking about reliability in terms of RowHammer together with on top of this. Is this that?
Yeah. So I'm saying that when you perform compute within the DRAM,
yes,
you are a lot more prone to bit flips due to RowHammer because you're activating a lot of lines for very long.
Yes, that's a funny thing actually. So yes, so initially when we first proposed the SIM-DRAM work, I think we are not so familiar with the blast effect of RowHammer. So and if you think about only RowHammer through like the adjacent rows, actually what we are doing when you do triple row activation is a refresh, because we always activate and then we precharge. And this is basically a refresh operation, which is what RowHammer mitigation solutions use to mitigate attacks usually, right? So if you don't consider that the blast effect, and only consider the compute rows that you are doing the computation, because this is the rows that you keep activating all the time. This is not necessarily is not more susceptible to RowHammer than regular DRAM, because again, you're just refreshing those rows constantly every time that you do a triple row activation. But then you have the blast ratio effect, right? Because if you keep activating rows in that compute row, okay, you are refreshing them, but what about the other ones that are sitting in the surroundings? And then we don't have a good solution for that yet, actually. Probably in theory, the current mitigation approaches should be able to mitigate that. So basically, in conjunction with RowHammer mitigation, I should just I'm doing my process using memory operations until I hit to a RowHammer vulnerable threshold, basically, right? And my memory controller should tell this control units stop. I need to do some refreshing to the other rows that are not the ones that you are doing computation, and then that stops.
Latency.
And then I resume after that, right? So that is more or less how mechanism should work. But of course, that would include some latency, because you need to stop the engine responsible for this computation at some point to refresh the other rows that you are not using for triple row activation.
Yeah, and since they are multiple rows, you have to perform multiple refreshes, which take hundreds of seconds each. Is this still overshadowing the time it takes to take things to the core?
I believe so. We didn't do the analysis, to be honest. We need to figure it out. But I think because the latency that you are talking here, usually for this these data-intensive applications is order of magnitude, the latency caused by this traffic is order of magnitude larger than the latency that we do actually by doing this triple activation stuff. So probably there is some slack over there that we can push this extra overhead latency, but further analysis needs to be done for sure.
Okay, thanks.
Thank you for the talk, and especially thank you for working on this Memory-RAM, especially for the fact that you did not stop at the micro architecture level and actually get to the programmers level. Thank you. So I want to say that can I assume that the compiler passes can be able to determine which operation needs to go to the CPU, needs to run, following up on one of the questions that was asked earlier.
Yes.
Like which instruction needs to run on the CPU and which one should just go directly to the RAM.
Yes. So I have a interesting thing to add to that actually. So initially, when I was developing this compiler, there was 4 passes, was not 3. The first pass, the second pass was responsible for cost model. So deciding, so I vectorize the instruction, right? And I have these two choices to do now as a compiler. I generate a process using the RAM instruction, or I generate a AVX instruction for that loop, right? And so based on some costs of doing that computation in the RAM versus doing that computation in the CPU, I'm going to try to predict which one is the best. It was way more complicated than I thought. Because as I mentioned before, I can know the latency of the portions of those latency components quite well. I can predict, but the bulk of the latency that would actually tell me to offload or not is dependent on the state of the system. So how many cache misses that particular instruction is going to generate at a given programmer count. So it's really specific. So I realized it was way too complicated, and I like, okay, this is a project by itself. And then we are still working on that. So what is end up being done in DRAM is that we always offload. And this is not always a good decision in terms of performance. So we see good performance per watt over here, energy efficiency basically, because we are eliminating that traffic. But for some applications, if you look at the paper itself, there is also raw performance numbers, and sometimes we actually end up slowing down the application. And this is because actually we couldn't amortize the cost of the CPU was faster, basically. We couldn't amortize the cost through this data movement of the computation. So there was not enough data movement to amortize the process using DRAM computation. But we are, as I said, we are still working on that. I personally believe that we need some type of runtime mechanism or a smart predictor to figure out that. There are engines that so in LLVM itself, there is a predictor of L1 cache misses or something like that, or cache misses already there. Exactly. But it's only for one level of the hierarchy. That is not the important one. The other ones are more important. And I tried to use that and was not that efficient because when you go with more complex access patterns, that predictor is not really efficient in the static time.
Okay, yeah, I think there are some works, actually some compilers that actually have done something on that.
Yeah. We can talk later, but yeah, it's a really complex problem.
Thank you.
Okay. There is a question over there. I guess this one does not work. The other one, okay, yes. Oh, neither of them work now. Okay, I can try to listen. Both of them die.
I wonder if you had tried to put the test coherence protocols like MESS DRAM banks
Because it's like interesting that if you do some processing using the memory, you can actually from the processor perspective, you can treat these DRAMs like they are not only the memory devices, and they are part of the memory coherency tree. And yes, if you put some MESI protocols into the memory controller or to the DRAMs themselves, and you can offload some of the atomic operations if they are not hit in the level 2 cache or the level 3 caches. You can offload some of the atomic operations into the memory itself. So have you done some researches on those domains? Like
not exactly what you mentioned. I'm going to try to remember exactly what you said, because this is actually a good research thing to check. But what we actually did is we did some works where we tried to figure out if you put the DRAM as one of the entities for Moese or MESI, whatever part of the coherence tree, what would be the overheads of that in terms of that overheads on top of the processing memory computation itself. And then we saw that actually the overhead is not negligible because basically like now you need to check for every single request, and like you have a lot of requests going on when you do this type of computation in bulk. And what we did in like was the PhD that graduated before me. He was actually working on this, and he did this lazy coherence for process using DRAM. So basically you speculatively assume that you can execute the computation in DRAM, and then you track using some bitmaps which words the DRAM access. And at some point, you compare which the writes that the CPU did, and then if there is a match, you roll back the computation. That works for Conda. You can mention later on. But for the atomic part, we didn't check.
Yes, I think it's also interesting that it's taken into consideration that if you whether you implement the optimic like the coherency part in the memory controller or the DRAM itself. It's like if you implement in the controllers, you will need to modify the controller itself. And for the DRAM itself, it's will introduce relatively high latency.
Yes,
and it's interesting.
Yeah. That's a really good. It's a really important and it's a research question that people tend to avoid. Because it's really difficult, and no one wants. I have this current problem with the research on process memory that people are not tracking the important problems because they are difficult. But those are the problems that are actually creating a barrier for the thing to be like fully realized. So is a thing that we need to figure out to push the state of the art further.
Okay, thanks.
Okay, so I'm going to try to finish up quicker so we can go for lunch, at least because the second part is going to be in the afternoon. So I'm going to just conclude this processing using memory portion. Just as a review, so we were able to do data movement operations in DRAM, Boolean operations and arithmetic operations, right? But there is a different type of operation that I didn't mention yet, that you're not able to do like using this type of substrate, at least not in a good way. Is that, does anyone want to give it a try to figure out what it is? Okay, I'm going to give the answer then because we have to go for lunch. So if you want to do a sine or a cosine or a log or exponential, all of those operations, you can approximate using arithmetic operations, but in general, those are hard to, they are not that accurate. You can do coordinate operations for transcendental functions itself, but they are not as efficient. So what is missing is to make the substrate more general purpose is a efficient way of implementing what is called these transcendation functions. The way that we are going to solve this problem is by using old idea, which is lookup table. So it's quite common, actually, like if you have a sign that if you have an embedded system, you just put a table with the most common angles that you are going to use inside inside a table inside your memory, your microprocessor, and other angles you just interpolate based on that, and then you just use that as a approximation. So what we are going to do is pretty much the same thing over here. So the observation is that these prior works have done all of these operations for process using DRAM, but the range for is limited, especially for these transcendation functions. So the goal of this work is to implement these arbitrary complex operations as needed inside the DRAM array itself. So the main idea, as I mentioned, is to use lookup tables. So instead of doing take the inputs using ALU in the computation, I'm going to store pre-computed versions of that computation in a lookup table inside DRAM. And then doing the execution, I'm going to consult this DRAM and get my output data. So this just means that I'm transforming computation into memory access now. This, as I mentioned, is a quite old idea, but we are going to realize that inside the DRAM substrate in an efficient way. So let's say that you have a computation where you want me to return to you, or the DRAM to return to you, the second, first, second, and fourth prime numbers. So 3, 2, 3, and 7. So we have this lookup table that has some indexes, and each index gives you the order of this prime number. So index 0 gives me the first prime number, which is 2. Index 1 gives me the second, which is 3, so on and so forth. So I'm going to, and I have an input vector which represents this query here. So I want the first index, I want the second index, I want the second index, the first index, the second index, and the last index. It's a bit confusing because one is 1 plus 1, the other one is not. And then I'm going to use this as an input vector, storing my sense amplifier. And I'm going to have the output vector, which should be represented of this prime number order that I want. And I have my regular DRAM subarray, and in the DRAM subarray, I'm going to have some extra logic. So I'm going to add this match logic, which is going to compare the index of the row that I'm accessing to the inputs of this input vector, which represents the order of the prime numbers. So I'm going to also store multiple copies of this lookup table inside the DRAM array in a vertical way, so that I can exploit parallelism. So the way that this is going to work is through what's called this Pluto row sweep operation, which is going to access each one of those DRAM rows in order and compare these indexes to the input vector. And if it's a match, it's going to trigger or assert some access transistors over here, which is going to enable me to copy the data in a particular location to this output vector. So let's see how it's going to work in practice. So the first step, activate the first row, which is 2, and recall that I'm looking for the second prime number, right? So it should be row index 1. Sorry, here I'm looking for the second, the first. So when I activate the data is copied to the row buffer as usual. And now my match logic is going to start asking questions. So am I accessing the second, I cannot see anymore, the second prime number? So 0 is equal to 1. This case is not, so that particular access transistor is not going to be enabled from the first position of my output vector. So am I accessing the first prime number? Yes. So my access transistor is going to be enabled. So it's a match. And the data 2 is copied to the output vector. So am I accessing the second prime number? The answer is not. And I'm not accessing the third prime number, so the answer is also not. So the only data that was copied was the number 2, which is the first prime number in this particular position over here. So this repeats for every single one of the rows. So the next time is going to be asking, I'm going to copy the last prime number, the number 3, the second one, and then the third one, and the fourth one. And then what you have in the end, in the output vector, is the output of this lookup table query that I did initially. So in the simplifier, I have 3, 2, 3, and 7. So in this work, we implement different ways of realizing this match logic and this output vector and this isolated transistors over here. I'm not going to enter in details over there, but what is important is that they have different trade-offs in terms of performance, energy efficiency, and error efficiency. So one trade-off is like one of the architectures is like it is the average of all of those three. The other one is better related to error efficiency, and the other one is better in terms of performance and energy efficiency, but bad at error efficiency. We also implement some system integration, so mapping this lookup table to applications through these ISA extensions and this Pluto compiler. Again, I'm not going to get into details here because it's a bit complicated. But what is important is that we take some applications and we map to the substrates, and we see that we can significantly improve performance compared to the CPU and the GPU and process near memory architecture. And this is even better if you normalize the values to the area. So if you take into account the DRAM is much smaller than the processor, for example. And of course, this also significantly improves energy consumption as well. So if you want more details on this, I invite you to check this talk. Is there any question? I went really quick here because of the time. I don't know if there's, it's more or less clear. Thanks. So, okay. Onur, I already talked about this. So all of what I mentioned before of this, not all of this, but we are doing studies in commodity off-the-shelf DRAM chips, and we are observing that actually we can do several of those operations on modifying real DRAM chips that are over there in the market. So in this study that we did in HPCA, and that Ismail did actually, we see that by violating DRAM time parameters of commodity off-the-shelf DRAM chips, we can activate multiple DRAM rows in neighboring DRAM subarrays. We can perform NOT operations of up to 32 operands, and we can do up to 16 input and NAND or and NOT operations. So just as a reminder, this is a DRAM chip that you buy in the market and you plug in your computer with a different memory controller, but it's a unmodified DRAM chip, just to see so this, all of this is feasible. So I'm not going to get into details on how this is done because I don't have much time, but you can talk to me or better to Ismail in the lunch break if you want more details on this stuff. So yeah, I'm going to skip this quickly so I can go through. I think Onur already mentioned as well, we have this infrastructure that is it's called PyDRAM, that is trying to ease the exploration of this commodity of the shelf DRAM chips from the software perspective. And this is open source, and we implemented some of those row copy operations over there, and then we see that we can actually do row clone and improve performance of real applications, of some applications using real DRAM chips. And again, all of this is available online, and you can check Ataboy's tutorial on this online. And just as a quick finisher, we can implement other process using memory substrate operations other than arithmetic or transcendental functions like unclonable functions through random number generation, and also this process use memory operations in other memory substrates like ReRAM, for example, Flash, which we are going to talk later in the end of the day. And I'm not going to get into details here, but just as this is an example of how this is done in other memory substrates. So I run substrate over here, which uses the Kirchhoff principle to implement do multiply accumulate operations in constant time. And people have been using this idea to do the neural network acceleration, because we can map the activations to different resistance levels and then do this quite efficient. So sorry that I rushed quite a bit in the last bit. I don't know if there is any burning question, but I managed to cover what I had intended in this first part of the lecture. So thanks so much for bearing with me. I don't know if there is any question, but let's take, otherwise you're done for now. So thank you so much.